minus half. Okay. So the three quantum numbers will help you. N will tell you the shell, L will tell you the subshell, and M will tell you about the orbital. And each orbital will have two electrons of opposite spin. That's what we had seen. One is known as plus half. It is written like this. Single electron is written by half arrow, or minus half is written like this. One can be considered equivalent to clockwise, another can be considered equivalent to anti-clockwise. So each orbital can hold maximum 2 electrons, and they should be of opposite spin. That's what we had discussed in the last class. So how to fill the electrons in an atom? There are certain rules, Navila, and those are they are actually clubbed together as under the name of Hofbauer principle. Hof was not the name of the scientist. It is basically the German word which means building up.
Yes, sir.
So what are we building up? We are building up atoms by putting electrons. How many electrons do we need to put, Maha? We need to put that many electrons which are there in the atom as per the atomic number. How do
It
you
can be
need to
any
put?
number, right? The electrons based on the
Yeah,
element.
it depends upon the element. Yes, it can be any number. Exactly. And we discussed in the last class that there are three rules. The first and the foremost is N plus L rule. Atoms are filled in increasing order of their orbitals are thus filled, orbitals and subshells are filled in increasing order of their energies. And how do you determine the energy? On the basis of the value of N plus L. Smaller the value of N plus L, that orbital or subshell is going to be filled first because it will have lower energy. If you are having higher energy of N plus L, that subshell is going to be filled next later on because that is having higher energy. If the two subshells have same N plus L, then the subshell having lower N plus L, lower value of N will be filled before, because lower value, if N plus L is same, the subshell having lower N will be considered to be of lower energy, and that will be filled first. So examples of N plus L values, okay. N is already written in front, and SPDF S is 0, P is 1, F is 3, okay. So you can have the value of L also, you can find N plus L, and accordingly you can arrange these subshell in increasing order of energy. One way is to find individual N plus L value. For example, here N plus L is 1 plus 0, 1. Here N plus L is 2 plus 0, 2. Here N plus L is 2 plus 1, 3. 3. So both have same N plus L values. So the 2p is filled before 3s because this N is smaller. 3p is N plus L is 4. It is larger than the N plus L of 3s. It is filled after 3s. Then 4s, N plus L is 4 plus 0. I hope you are getting my point, everybody.
Yes, sir. Yeah.
Okay. Just a second. Let me start the camera also. I'm trying to start. Yeah. So this is N plus L rule that helps. Or there is one more way. You write these orbitals, subshells very symmetrically. 1s, then second shell will have 2s and 2p, third shell will have 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay. But you have to be very draw them very neatly. Got it? Don't if you draw them in a haphazard way, okay, and you need to put this arrows moving from the top right hand side towards the bottom, slant arrows, okay, cutting these orbital diagonally, moving from top, got it, and going
Yes.
toward downward. So they can tell you the value of n plus l. Means instead of uh, finding numerically, you can just follow these arrows. So 3D is filled, then 4P, then 5S, then you go back, then 4D, 5P, 6S, okay, like that. Is it clear?
Yeah. Yes, sir.
Okay. So I hope up to this point everything is clear, and each orbital can hold maximum of 2 electrons, and they should be of opposite spins, right? So we were doing electronic configuration. So hydrogen, one electron is there, atomic number is 1. We will put in 1s, got it. We will put in 1s. Helium is having 2 electrons, okay, and I'm going to put it in 1s only because each orbital can hold maximum of 2 electrons, and they should be of opposite spins. This is Pauli's exclusion principle. That what we had discussed in the last class. Okay. Orbital cannot have 3 electrons because if you try to put 3 electrons, the 2 will have opposite spin. The third one need to have spin same as either to that of first or second. So all the spin should be different. So each orbital can hold maximum of 2 electrons, and they should be, one should be spin up or down, and another should be spin down, means one should be clockwise, another should be anti-clockwise. That
So I
I
don't
hope.
understand this at all.
Yeah, and I'm again telling, don't worry. So each orbital can hold these orbitals are represented as boxes, okay, instead of drawing that P and D, got it.
Okay.
So lithium, for example, it has 3 electrons. So how am I going to put these 3 electrons? In 1s, the spin can be clockwise or anti-clockwise, which can be represented by up and down. But if I put the third electron, it will be like this one. Either it will be like this. If it is like this, that is also not acceptable because its spin is matching with this electron.
Yeah.
So this Pauli's exclusion principle tells us that each orbital can have 2 electrons and they should be of opposite spins. Or there is one more way to tell that no 2 electrons should have same value of all the 4 quantum numbers. So if the shell is same, subshell is same, orbital is same, it means n is same, l is same, m is same. So at least they should have different values of spin quantum number. One should have spin plus half, another should have minus half, and if I try to put all the 3 electrons of lithium in 1s, see what has happened. Out of the 3 electron, the last electron has spin same as that of the second one, so it is not acceptable. So I need to move towards the next subshell, that is 2s. Got it?
Yes,
Maha,
sir.
is it clear? Nabila, is it clear? Okay. Beryllium is the 4th element. Okay. So I still there is one space for one more electron, extra electron in 2s. I put the 2s, that extra electron, 4th electron in the 2s. But remember, this is of opposite spin. Okay, one is spin up, okay, clockwise, another is spin down. Okay. Otherwise, they are going to repel each other and they are not going to be stable. Boron is the 5th element. So 2 electrons I put in 1s, 2 in 2s, and the 5th electron I have chosen because I can't put that 5th electron in 2s subshell. As you know that each orbital can hold maximum of only 2 electrons. Okay, and they should have opposite spins. Is it clear or not?
Yes.
So
Yes.
as you can see here that I need to move toward 2p subshell because 2p subshell that is empty. So I put that one electron into. I can put in 2px, 2py, 2pz. I put 3 boxes in 2p. This is 2p subshell will have 3 set of. It consists of 3 orbitals. One is along the x-axis, another is along the y-axis, and another in the z-axis. 2px, 2py, and 2pz. Got it?
Yes.
I hope this is clear to all of you.
Yes, sir.
This is now we need one more special rule out of those 3 rules. N plus L tell us whether to fill 1s or 2s or 2p. Once you have that, how many electrons you are going to put in one single orbital? That Pauli's exclusion principle will help you out that you can put 2 electrons but with opposite spins. Okay, then you need to uh, move in order to write the electronic configuration of the next element, which is the 6th element, which is very famous, carbon. You need one more extra rule. Why you need one rule? Because 6 electron, 1s will have 2 electrons. Got it? 2s, 2 electrons. Got it?
Yes.
And 2p will have 2 electrons. If you write it like this, it is okay. It is not a problem. Or you can write it like this. The inner electrons can be written, can be represented by writing the symbol of the preceding noble gas, which is the helium. Got it? But the problem rises if I ask you to show the detailed electronic configuration with orbitals. Okay. So you can, for 1s, there is just one orbital because for s, L is 0, M is also 0. The value of M is 0 only. Just one orbital, so you put 2 electrons in 1s with opposite spins. Here the problem will start. What will be the correct electronic configuration of carbonate? I am giving you various options A, B, C, D, E. You need to tell me. And for this, there is a rule which we have not yet discussed. And that rule is Hund's rule of maximum multiplicity. Pauli's exclusion is about the opposite spins of the 2 electrons in same orbital. N plus L is about the choosing the subshells.
So
In
what does
proper,
maximum multiplicity mean?
yes, I'm coming to that. Okay. So first we will think of what many possibilities can be there. Are you getting my point?
So
In
possibilities of what?
possibilities of putting 6 electrons in 2p subshell and orbitals, respective 2p orbitals. Getting my point or not?
Yeah.
So which one is correct? Which one is
First one.
first one is correct?
Yeah, first one.
Okay. Suppose all the students are going on a picnic in a bus. So normally what happens? Everybody try to capture
We sit beside our friends.
window seat or one another. It
Window seat.
depends actually. Yeah, window seat. Yes, exactly. And they all face in the same direction. They don't sit in the back direction normally. I'm assuming a normal bus where all seats are pointing in the front direction. So same way, if there is a subshell and electrons are put in the subshell, the subshell, this problem arises when you have a subshell which consists of more than one orbitals. It doesn't arise in S because there is only just one. Okay, got it? S is just like a two-wheeler. Two-wheeler, two persons can sit. Okay, they should sit and they should go, right? Suppose 2p, there are three orbitals. So how they should be filled? First, each one should be filled with single electron and parallel spins. With parallel spins. Are you getting my point? Ohm's rule of maximum multiplicity I'm telling in a layman language, then I will tell you the exact. First try to understand. When you are filling the orbitals belonging to same subshell, which rule should be there in your mind? Ohm's rule of maximum multiplicity. Got it? And
Okay.
what it says, and what that rule says in a common man language, that if you have multiple orbital within a same subshell, each orbital should be filled first with single electron and with same spin. Once all the orbitals are half filled with electrons, single electron, half filled means single electron, then the pairing should take place. Okay. So, is the first option correct? A option correct? Because carbon, I put the 4 electron, the fifth and sixth electron. What I did, I'm putting these last two electrons in the orbitals belonging to the 2p subshell, and the 2p subshell has multiple orbitals, as you know. 3 orbitals are there. So the Hund's rule tells us that these orbitals should be filled first with single one electron each with parallel spins, and once each one has that single electron filled, then you should start the pairing. Okay, you should not pair directly. Just like I gave the example of a bus, where first the student tried to occupy the window seat. Okay, once
So
the
is
window
it
seat
D?
are, pardon?
Is it D then? Like I'm confused with the B and D because one arrow is two
Yes,
arrows
yes,
are
yes,
up
yes.
over
Yeah,
there.
yeah. So B is correct, exactly. So if there are multiple orbital within the same subshell, they should be filled with one electron each with parallel spins. So B is correct. Parallel spins also you should keep in mind. Is C correct or not? C is also correct. somebody can go and at the back seat and can sit near the window. Okay, parallel spins, you should keep in mind, this is incorrect. Why? Because the
Opposite
spins are
direction.
opposite directions. Okay, and this is also incorrect. This is violating two rules. What are the two rules which this electronic configuration is violating? What are the two rules which this electronic configuration is violating?
Both are
The
opposite
electrons
direction.
are supposed to be in opposite facing, spinning in the
Yeah.
opposite direction, but over here it's the same.
Yeah. Each orbital should have electron in up with opposite spins, and that rule was given by Pauli's exclusion principle. That no two electron should have same value of all the four quantum numbers. If they are in the same shell, subshell, and orbital, they should at least have opposite spins. Okay. So you may have question in NEET. These are the favorite questions of NEET and CBSE and everywhere. So which rule this is violating? This is violating Pauli's rule. Got it?
Yes, sir.
And this is also violating Hund's rule of maximum multiplicity. Because Hund's rule tells us that orbitals belonging to a same subshell should be first filled with single electron with parallel spins. Okay, and you have put a two electron in one orbital only, though you have still two uh, more orbitals of the same energy of the same subshell left. Okay, so it is also violating Hund's rule. Ravila, is it clear? Maha, is it
Yes,
clear?
sir.
So both the rule are being violated. Got it?
Yes.
So you can either you can you can also point them downward. Like this is also correct. It doesn't matter. But they need to be singly occupied first. Once all are singly occupied, then you will start pairing. Got it?
Yes, sir.
Yes, sir.
Okay. Now we will move to the seventh element. So I will write the rule also. Ohm's rule. So different orbitals belonging to a same subshell are filled by one electron, single electron with same spin. Pairing will not occur until each orbital is occupied by one electron. Okay. Once all the orbitals have one electron, then you will think of pairing. And if you have more electron, then you will go for pairing. Now we will move to the seventh element, that is nitrogen. And the seventh element, I will write it directly. Nabila, can you help me out? Oxygen, Maha, you will be helping me out in oxygen. Nabila, you can help me out in the electronic configuration of nitrogen. 1s2, 2s2. Okay.
Yes.
And now you have 2p subshell. 2p subshell will have 3 orbital, 2px, 2py, 2pz, and how I'm still left with 3 more electron. And
The
how I'm
same
going to
one
put, yeah,
in
I'm going
each
to
node.
put one in each with parallel spins. Maha, is
Yes.
it clear?
Yeah.
Okay, now you can help me out, Maha, to fill electrons in oxygen atom. How many electrons in 1s? How many in 2s?
So first you can fill the first two boxes with like the opposite arrows.
Yeah. Then 2p. 2p first I will fill with
You can
one
fill
electron
each
each.
of them with but one electron pointing
Yeah,
upwards.
yeah, exactly. But now I'm having still one more electron left because total electrons were 8. So now I can go for pairing. Got it?
Yeah.
That's what I said. Pairing will not occur until each orbital is half filled, or half filled means singly occupied. Half filled means just one electron. Got it? Then you have
Yeah.
fluorine, which is the ninth element. I will write it like this: 1s squared, 2s squared, 2p x 2, 2py2, and 2pz1. You will have 2 electrons being paired in 2p. Got it? Then neon, which is a very important landmark because it is a noble gas. It is a completely filled electronic configuration, and that is 1s, then 2s, and this. Because I'm having 10 electrons, so all the 3 2p orbitals are filled. Okay. So as you can see, I can quickly recap. If there is the shell, nth shell, how many electrons it can have? It can hold maximum of 2n square electron. You can verify it now itself. The second shell will have how many electrons? N is 2. So 2 into 2 square, 8 electron, and you can see there are 8 electrons. Got it?
Yes, sir.
Second shell will have how many orbitals? I multiplied by 2 because each orbital can have 2 electrons. So to get the electron, I multiplied by 2. To get the orbital, just remove the 2. You have n square orbitals. N square is how many orbitals? And subshell, n subshells. two subshells. Two subshell, S subshell and P subshell. Got it? Clear? N square orbitals.
Yes.
For example, 2p. 2p, if nothing is said, it is 2p subshell. Subshell actually consists of a group of orbitals with different directions. What is the value of n? N is 2. Okay. What is the value of L? Okay, L is 1. L starts, as I told, I was explaining Nabila in the last class. L is the secondary quantum number, subsidiary quantum. But you should start counting from here. 0, 1, 2, 3. Normally we count like this 1, 2, 3. Okay. 0, 1, 2, 3. Okay. S, P, D, F. Got it? So L is 1, L is 0 is S. Okay. L is just one step down from N. Okay. So this is the P subshell. What is the shape of P subshell? There is a name to it. Dumbbell shape, right?
Yeah, double shape.
Got it. This is the general shape, but S subshell is not
8
just
shapes.
not just one. It consists of group of three orbitals, the electron clouds. Okay, and what are those three orbitals? They have, because L is 1, so for 1 you can take M. M will have M value of M will vary from minus L to plus L. Actually, you put in that Schrodinger wave equation. When you put 0, you get Pz. When you put 1, you will get a P orbital, which is in, when you solve it mathematically. But because we are not solving it mathematically, we can just remember that the value of M varies from minus L. Minus L means minus 1 to plus 1 through 0. So three different values. Okay. So whatever the value of P, okay, whatever the value of L is there are 2L plus 1 orbital. The number of orbitals in a subshell will always be odd, 2L plus 1. For example, there are 5 D orbitals. Got it? Px, and they are in different direction because the p orbital directions are quite simple. They are along the x-axis, y-axis, or z-axis, so their name are quite simple. Px, Py, Pz. You can call any one of them like that. Py, Pz. Got it? Is it clear?
Yes.
Now we will
Yeah.
move towards the 11th element, sodium, magnesium. Na is the 11th element. So 1s square, 2s square, 2p6. I'm going to follow that neon. And now the second shell is completely filled. I need to move toward the third shell, 3s1. Or you can express any electronic configuration in terms of, in short and representation. You can represent the inner electronic configuration in terms of preceding noble gas. Got it? So preceding noble gas was neon, but you should not directly do it. You should do it after, once you have the practice. Okay, so I initially will ask you to write it like this. Okay, once you are quite confident with this method, you can move to this method. Later on, you can just write this. Got it? Na, okay, Mg, all of Mg, I can, it is a 12th element. Neon means this part is neon. Okay, so this is going to remain same, 3s2. Aluminium is the 13th element. Is it clear?
Yes, sir.
So whatever the thing is, the important screenshot would you like to take, you can take it. You can just ask me. so that you can quickly revise that. You can also, you must be writing it also. So this is 3s2. Aluminum is neon, and neon is 10th element. Okay, this is 3s2, 3p1. Got it? Similarly, you have silicon and all. This is the third period. Silicon is there below the carbon. If you compare the elements one below another, for example, if you compare boron and aluminum, they are in the one group. Boron was helium. It was the fifth element. Okay, so two are there in the 1s2, 2s2, 2p1. If you compare the element one below another in the same group, okay, aluminum is the 13th element, so it is helium, it is neon, okay, and 3s2, 3p1. So if you are comparing the element one below another, most of them, there are few exceptions, okay, have same electronic configuration, same type of electronic configuration, not same type of valence shell electronic configuration. Their shell number will keep on increasing. This is the from the second period. So the shell, outer shell is second shell. This is from the third period. The outer shell is third shell. Got it? You have the same type of valence electronic configuration. Okay, you can see that there is 2s2, 2p1. Then for aluminum, you have 3s2, 3p1. Okay, below aluminum, you have gallium, which is the 31st element. Okay, this is from the fourth period. Got it? So, what will be the valence shell electronic configuration? Valence outer shell electronic configuration of gallium, it will be 4s2, 4p1. Got it? It is from the fourth period. Is it clear? So
Yeah.
elements one below another will have same outermost valence shell electronic configuration, and so these are from the same group, and that's why they have the same chemical properties, because their outermost electronic configuration are same. Clear? So you can practice up to calcium. After calcium, I need to discuss again because there is some new thing which is coming up. Calcium is the 20th element. Okay. So if I start writing its electronic configuration, it will be 1s, 2 electron in the first shell. Second shell will have s and p subshells, and it will have 8 electrons in the second shell. What it I am writing the detailed electronic configuration. Until now, I have put 10 electrons. 10 more I need to put because the atomic number is 20. Then I move towards 3s. Got it?
Yeah.
3s will have 2 electrons with opposite spin. Then I will move toward the 3p, and 3p will have 3 orbitals. First, I'm going to put 1 in each with same spin. Then I'm going to pair them up, and at max, six electrons will be held by 3p. Got it? This is, I hope, clear. Until now, I have put 18 electrons. Okay. This is the electronic configuration of argon. Let me tell you very small trick, very important, and it will make your life very easy. Remember the atomic number, electronic configuration of each noble gas and their period. They are like their landmark.
Oh, what can I repeat?
Yeah. Remember the atomic number and the periods of all the noble gases.
So what do you mean by periods of all the noble gases?
For example, Yeah, that detail I'm going to discuss in the next chapter of periodic table and properties. Period is the horizontal lines. So helium is the first period. Helium, neon. Neon is atomic number is 10. Argon 18. This is from the third period. Second period. Okay. The horizontal rows are known as periods. Got it?
Yeah.
Krypton 36. One. This is in on fifth period noble gas. Fifth 54. Radon 86. Sixth period. Got it? And seventh period is the last period and the last noble gas organism OG 118th element. This is recently discovered. Why am I telling it? Because suppose somebody may give you atomic numbers 57, 98, like that. Okay. So what you can do is, suppose if somebody give me 38, so I can start like this. Because 36 and then this. Fifth period 5s2. This is the electronic configuration. Got it? So I'm going to discuss in more detail in the next chapter also. But as of now,
So I didn't understand this.
yeah, I will let you understand. As of now, what you can do is you can remember the noble gases, their atomic numbers and their period numbers. Okay. This will help you out to they are just like the milestones. Okay. Suppose if I give you atomic number 37, what is the electronic configuration of the 37th element? What is the electronic configuration of rubidium, which is the 37th element? Tell me. So either you will start from 1s2, 2s2, 2p6, 3s2, 3p6, okay, like that. Okay. But what I told you, I told you to remember the noble gases, their atomic number, and it will come to your mind, okay, 37, the noble gas just before it is krypton. So you can quickly figure out the inner electronic configuration is same as that of krypton and one more. So that fifth shell is going to start from 5s. Each shell starts from s. Okay. So and one electron. This is the electronic configuration.
Okay.
Got it? So it will save your time. Got it? I will discuss it in detail. I will tell more tricks. But as of now, remember the noble gases and their horizontal rows, which is known as period. Got it? It will save your
So
time.
how many elements and their atomic numbers do we need to remember?
30, up to 30 you can remember.
Okay.
Okay, up to 30 you can remember, and that will be sufficient, right? And there are certain individual atomic numbers which we need to focus on, that we will be discussing in the next chapter of periodic properties. So let me move towards the beyond calcium. Okay, I need to, from 20 to 30 I need to discuss. This is very important. Okay, calcium is 22. Now remaining 2 electron, where should I put it? In calcium I have put only 18 electron till now. Argon, 2 electrons are still pending. Where should I put it after 3p? Third shell is having 3 subshell, 3s, 3p and 3d. Should I put it in 3d or 4s? So till now what we were doing, whenever we are jumping on one shell is complete, we start from s. So what should be the electronic configuration of the calcium? Is it 3d2 or is it 4s2? Are you getting my point? Nabila, are you getting it?
4s.
Now I am having how many electrons? I need to put 20 electrons. Okay, 18 I have already put, and third shell is having 3D, and there is fourth shell also. The remaining 2 electron of the calcium after the 18 electrons, should I put it in 3D or 4s? Why, Maha, you are considering 4s? Why not 3D? Nabila, what is your view? You can also tell me.
I'm not sure, sir.
No, just think of the rules of the principle. There were 3 set of rules.
Oh,
While
sorry, sorry. It's gonna be 3D square, right? Because first S, then second SP, then third
yeah,
SPD.
okay, normally SPDF, that's how we say. Okay, because each 4 shell will have 4s, 4p, 4d, 4f. Got it. But how to choose within the subshell? There is a rule, N plus L rule. Subshells need to be filled in increasing order of their energies. Okay, a subshell having lower energy will be filled before the subshell which is having higher energy, and I'm not going to calculate the energy. Okay, I'm just going to get the idea of their energy, whether it is higher or lower, by comparing their which value, N value, L value, N plus L value, which value comparison of which value of these subshells will help me out to figure out which subshell is having lower energy. Nabila, are you getting my point or not? So which one should I choose? 3D should I choose, or 4S? But normally there is 3S, 3P, and after 3P there is 3D. But which one should I choose? But we will not go by normal intuition. We will verify it first, and then what value we need to verify. Maha. We need to verify N plus L values. Okay. This is N plus L rule. 3 rules were there, which we discussed. Lower N plus L value means lower energy. If the subshell is having lower energy, that is filled prior to the subshell having higher N plus L value, which represents higher energy. Is it clear or not?
Yes, sir.
Got it. So normally we say C 3S, 3P, 3D, but don't go by normal intuition. Verify it. Ma, is it clear?
Yes, sir.
So 3D and 4S. So what are they in N plus L value? N is clearly visible 3. And D, what is the value of D? Look here. I start from this division. This is not my finger, this is my palm. 0, I call it 0. S P D D L L. For L, I start by counting from this point. Okay, this point is 0, 1, 2, 3. This is my way of doing. This is not a standard way, just my way. If I'm doing it, S P D L is 2. Got it? That's how I do it. So 5. You can also do S P D F. F is L is 3. G is 4. Okay, like that. I count the L, S B D F, value of L, and this is the 4S. So 4 plus 0. What is the N plus L value? 4. Now you have the N plus L values written in front of you. And after 3P, which subshell need to be filled first? Can you tell me? 4S or 3D?
3D.
3D or 4S? The one which is having lower energy.
Yeah, 4S.
Yeah, lower energy means lower N plus L value. So it is the 4S. though there is a 3D subshell, but in spite of that, we are strictly going to stick on to n plus l rule maha. Is it clear or not?
Yeah.
We are not going to go by normal way of filling that 3s 3p 3d. Okay, we are going to leave it empty. Okay, because we are strictly going to stick on to n plus l rule. So the electronic configuration of calcium is not 3d2, it is 4s2. What reason will you tell? It is because of the n plus l value. The 4s is having lower n plus l than 3d, so it is filled prior to 3d subshell. You should be clear in explaining. Got it? The shortcut representation, as I told you to write, but don't write it before first, because I want you to do practice, then move towards the shortcut. Okay, the preceding noble gas is argon. Normally I write it like this. I don't do this much thing. Okay, and 4s, but you can also write it once you are confident. Then you can write this, written this. Clear?
Yes, sir.
Yes.
Now next 10 electronic configurations are very, very important. Scandium, titanium, vanadium, chromium, manganese. Then you have iron, 26th element, cobalt, nickel, copper, zinc. You can remember the mnemonics. You can make a song C, TV, Karman, Fekoni, copper, zinc, like that. Okay. These are very, very important. So 21st element, and I'm going to write the inner electronic configuration in the terms of argon only, because I'm going to want you to understand the outermost electronic configuration. Inner you can practice. So what will be the electronic configuration of scandium? Argon, after
4s
4s,
square TD.
yeah, 4s you have 4p. Is it, should I go by normal way what comes after this, or should I follow the n plus l?
So can you repeat?
Should it be like this, or is it correct? 4s 4p. And remember, we skipped some subshells in calcium. What will happen to those subshells? What was the subshell which were skipped in calcium? We skipped 3D. Should we fill them here?
Yeah.
Should we start filling them in scandium? We can't keep them empty. Okay, we need to put electrons. So the 21st element scandium, the 21st, because inner electronic configuration will be same as that of calcium. The last electron, the 21st electron, is it going to come in the 4p or 3d? Who is going to tell me, Nabila? Which rule will help me out? N plus L rule. Got it?
Yes, sir.
So what are the N plus L values? Maha for 4p and 3d. N is 4, that is clearly visible. SP.
Phase 2.
No, and SP. No, that's why I start from 0. Okay, this is 0. SP 1. Got it?
Yeah.
Can you see my hand? Normally we count like this: 1, 2, 3. Okay, this is my way of counting: 3, 4, 5, 6. Okay. For subshells, I start counting from this division 0. S, P, D. Okay. F. So S is 0, P is 1, D is 2, F is 3. Got it like this. In quick manner, I don't make mistake like this. SPD. SPD, I start counting from this. Okay. This is 0th division, not the division of my finger. Got it? Is it clear or not? So normally I have seen a student making mistake every time. So I call them like this. Like, just start your counting from S, P, D, F. Okay. G, H, I.
Okay.
Just start from this S. Okay. P is 1. Got it?
Yes,
I
sir.
hope this is clear. So 4p is 4 plus 1. What is the N plus L value? N plus L, 4 plus 1, 5. 3D, what is the N plus L value?
Five.
SPD, yeah, 5. Both are equal, N plus L. So which one should we choose? If the N plus L values are same, then we will choose the subshell which is having the lower value of N.
So 3D.
3D. Okay. Is it clear?
Yes, sir.
So what is the electronic configuration of scandium? I will write it argon, but the 3D is inner subshell. Okay, it is filled after, it is inner actually. But it is from the third shell. So I should write it like this. But third shell start filling after 4s. The D subshell, not the third shell, the D subshell of the third shell start filling after the 4s. Is it clear or not?
Yes.
Yes, sir.
Because it is inner, I have written it inside. Then everything will be okay. Titanium, vanadium, that will be okay. Argon, 3D2. But how you are going now? There is one more doubt, but I hope you will be able to figure it out as we discussed. 4s2. The doubt is because how we are going to put, how many orbitals are there in the D subshell? First of all, tell me. Number of orbitals are always odd. Okay. S was having just one orbital. 2L plus 1 orbitals, different color. P was having 3, D was having 5, F 7 orbitals are there, 7 boxes. Got it? So, and there are 2 electrons, then 4s2. Okay. S, no need to, because in X there is just one orbital, one box, just we can put them in opposite direction. These 2 electrons, how we are going to put? And which rule is going to help us out? while filling electrons in the 3D subshell orbitals belonging to 3D subshells. What was the rule? Yeah, Nabila?
Yes, sir.
No. N plus L we have already chosen that 4s is filled and 3D.
Once per.
Ohm's rule of maximum multiplicity. Got it?
Yes.
You need. So if you are filling the orbitals belonging to a subshell, you should fill them with one electron each of parallel spin. Okay. Then once they are filled with single electron, then you are going to pair them. Got it? Is it clear or not?
Yes, sir.
This is titanium, vanadium. What is the electronic configuration? Argon. Okay. I'm writing shortcut method, but you should practice it in detailed manner after the class. Okay. Should I start pairing the electrons? No, because 4s I have paired them up. Just one orbital was there. In D you have multiple orbitals, so let them remain unpaired with. Let them fill with one electron with parallel spins. Okay. Chromium. Chromium is a bit problematic, and this is chromium and copper. They are very, very important, and the questions are being asked. So chromium is the 24th element. Chromium is exception. An exception means there is something wrong with this. That's why it is an exception. Okay. We are not going to write this electronic configuration. What we are going to do, we are going to move one electron from 4s to 3d. So just read it out. Navila, could you please read it out for me?
It prefers extra stable half-filled D subshells.
Yeah. So what is happening? Why it is happening? That I will tell. So what is happening over here is, so ideally the chromium should have this kind of electronic configuration: argon 3d4 4s2. The best way to remember the electronic configuration are for 21 to 30. For example, if you're 24, so what you will do? You will write 4s2 and 3d4. 25, 4s2 and 3d5. Got it? 26, 4s2 and 3d6. That is the shortcut way of writing, remembering. But in chromium, the shortcut goes wrong. This is not the electronic configuration of chromium. Instead, it is like this: argon 3d5 4s. Got it?
Yes, sir.
It is just electronic configuration, and the reason I have superficially I have written it like this. Maha, what it means actually. Can you help me out? What can you infer from this? So D subshell was having just one electron short of 5 electrons in chromium. So when these subshell, so you are just having one. This you are going to do it in D subshell only, in chromium and copper only, not in other elements, not in other smaller elements. So what you did, as per this statement, is half filled and fully filled subshells are very stable in their electronic configuration. So what you did, you moved one s electron. How can you get it half filled? You can't bring in 26 electrons. This is chromium, which is having just 24. So you can't bring one extra electron. So what you did, you moved one extra electron from 4s to 3d to make it half filled. These half filled electronic configurations are stable. So you have moved one electron from 4s. So this is the exception. Till now we were having two electrons in from calcium. You were having two electrons in calcium, scandium, titanium, vanadium, chromium. Also, it was expected that two electron will continue to remain in 4s, but chromium was having just 4 electron in D subshell. Just one electron was more needed to make it half filled with one electron each. Okay, so you can't get that electron from outside. You just move that 4s electron from the outermost 4s to inner 3d, okay, to make it half filled. Why you did it? You will write due to extra stability of half filled D subshell. Okay, this is the outermost way of saying it. Is it clear?
Yes, sir.
Yeah.
Why chromium is not 4s2 and 3d4? Why you have moved, and you are not going to do it for all set of electron, just one electron. If you are just having one electron short, you will move it from the adjacent and make the D subshell half filled or fully filled, right? That fully filled thing is going to come in the copper. This is very stable. So if somebody asks you why it is happening, why the chromium is not 20, so chromium was 24th element, so it should be 24 means 2 and 4, 4s2 and 3d4. Why it is not like this? Why it is 3d5 and 4s2? What you will write? The thing which will most easiest way of writing the wholesome answer is due to extra stability of 3D or subshells. Extra stability of 3D orbitals. One electron has to be moved from 4s to 3D to make it half filled with one electron each. Why it is? So this is the outermost reason. Okay, means this is the superficial uh, reason way of saying it, and that can help you to get good marks. Okay, due to extra stability of half filled these orbitals. The actual detailed reason is that when you have these electrons, when they are in the orbitals belonging to same subshell, what they do is they tend to exchange their positions. What happened? Suppose you might have played a game which is, you might have seen a game where some kids, or you may have also played that, you go and occupy a corner and there is one person who just stand in the middle and you try to exchange your corners. Okay, got it? Maybe I don't know whether you have played it or not. So this person is standing in the middle will try to get and occupy the corner if it is empty. Okay. So the people at the corner exchange their positions with each other. Similarly, the electrons within a subshell exchange their orbitals. Okay. I'm not exchanging the 3D with 4s. Okay, 3D with the 2p. Okay, the 3D or 3D because they are of equal energy. So they keep on exchanging. So how many exchanges are possible? First electron can exchange its position with 3 other electrons. So 3, and this electron can exchange its position with the remaining 2. It has already exchanged. I have considered with the first 2 plus 1. Got it? 3 plus 2 plus 1. How many exchange? 6 exchanges. And in this, the first electron can exchange its position with 4. Second can exchange with 3. Okay, this. 2 plus 1. So total how many exchange? 10 exchanges are possible. These exchange happen. Okay, they interchange their within the orbitals belonging to same subshell with equal energy. So they tend to become stabilized by this. Okay, they attain stability. So you are going to say why the chromium is not 3d4 and one electron is moved from 4s to 3d to make it 3d5. It is because one thing which you are going to say is due to extra stability of half-filled d subshell, the half-filled d orbitals with one electron each, all having one electron each, is more stable. First, you are going to write that statement. If somebody asks you why they are more stable, you are going to write that because of the higher number of exchanges, the D5 subshell will have more exchange energy, more extent of stabilization, more exchanges means more extent of stabilization than D4, which is having less number of exchanges taking place. 6 exchanges and there 10 exchanges just by moving one electron, and these exchange release energy. So that is a more detailed way of saying it. Got it? So tell me which part need to be explained again. Maha, Nabila.
So the exchange part.
Exchange part actually, you need to understand that the electron, they keep on exchanging their positions within the orbitals belonging to same subshell, and more the number of exchange, more will be the energy which is released and more will be the stability. Got it? So if you had just D4, okay, there were 6 exchanges happening between the electron possibilities, and when you move just one electron from 4s to 3d and to make it 3d5, so 5 electron can, there were 10 exchange. This electron can exchange with 4, this electron can exchange its position with 3, this electron can exchange with 2. Okay, so actually you need to count the number of exchange. These exchange release energy. Okay, they make the electronic configuration more stable. This is an entirely different part, okay, different rule actually. Okay, but every time we are not going to consider it. It is happening at many places. but it is going to play its most prominent role and affect the electronic configuration when you have 24th element and 29th element. Is it clear or not? Got it? So you need to remember it. There is a superficial way of saying which will help you to fetch marks. That is why chromium is 3D5, not 3D4. The superficial way of saying, which is the correct way, that due to extra stability of half-filled D subshells. But if somebody asks you why the half-filled D subshell with 5 electrons is more stable, then you are going to say that in half-filled D subshell, there are 5 electrons and they're going to exchange their positions. More number of exchanges, 10 exchanges are possible as compared to D4 where 6 exchanges were possible. So that's why the half-filled D subshell with 5 electrons undergoing 10 set of exchanges are more stable. They have more exchange energy being released and they have become more stable. Is it clear? That's that due to higher exchange energy. You don't need to explain each and everything. 10 exchanges, higher exchange energy is released, and that's why D5 became more stable than D4. You need to say it in this much. I will explain it to you again in the copper. Iron, it is as usual, there is no exception. Argon, 26. What is the trick? 26 means 2 and 6. 4s2, 3d6. Got it? Very easy to remember. Nabila. Maha, cobalt is 27th element. Argon, then 2 in the outer and 7 in the inner.
Oh, okay, I get it now.
Nickel is 28th. Argon, 2 and
So
8.
3D raised to 8, 4s is
29th. Argon, 2 and 9.
3D raised to 9.
But again, there is a problem here. The same problem which was there in the one shot of completely filled. That was one shot of half filled. This is one shot of. So I will get back to the problem. Let's complete zinc. So 30 is 4s2 and 3d10. Got it? Argon, 4s2 and 3d10. So what is the exception in copper that you are having this not 3d9, but instead of 3d9 you have 3d10? What reason will you say? Superficial way of saying an answer and a statement which will fit all conditions, all set of conditions, is you will say that it is extra stable. D10 is extra stable. So what you are going to do, how you are going to make D9 as D10, you are going to pull one electron from the 4s and make 4s1 due to extra stability of fully filled D subshell. But if somebody asks you why it is extra stable, you will say because of the symmetrical electronic configuration and more number of exchanges happening with 10 electrons instead of 9 electrons. Is it clear or not?
Yes, sir.
If you are asked to calculate the electronic configuration of the ions, you are going to remove the electron. So if you have positive charge, you are going to remove the electron, but always remove the electron from the outermost shell. Is it clear or not?
Yes, sir.
What is the electronic configuration of titanium?
So we didn't do 25.
Titanium was 22. Second element, so argon 22 was 2 and 2, right? 4s2 and 3d2. But while removing, you remove the outermost shell electrons first. 4s you remove 3d2. It has 2 unpaired electrons in D substance. All the inner are paired. N is the number of unpaired electrons. And these each electron, because it rotate and clockwise, and that's why you put the spin up or down to represent their spins. They behave like a magnet. So it will have a magnetic behavior, it will get attracted by the magnetic field, it is paramagnetic. Paramagnetic is a substance which get attracted by the magnetic field. And that happens if it is having unpaired electrons, substance with unpaired electrons. Because each electron behave like a small magnet. You might have done experiment in your class 10 that when you wound a wire around a nail and you pass electric current, it requires magnetic current. Same thing here also. Got it? So I hope this is clear.
So
And
manganese.
Manganese is having Mn2 plus is having 5 unpaired electrons. Mn, yeah, Mn is, I left. Yeah, Mn first I can write Mn25. So argon 25, 2 and 5, very simple. 3D, so 4s2 and 3d5. That's one. Mn2 plus is 3d5. So Mn2 plus is more paramagnetic than titanium because Mn is having 5 unpaired electrons. Okay.
Yes, sir.
So this chapter is complete. Next chapter, what should we start? Periodic properties. Yeah, Maha, Nabila, tell me quickly. So we can start with the periodic properties. Okay. In the next
Okay.
class. Okay. Okay. Bye bye. Take care.
Thank you, sir. Bye.